All right, let's get into it. You know, behind the walls of your house, there's this incredibly complex web of wires, and it's all governed by a massive rulebook called the National Electrical Code, or the NEC. Today, we're going to zero in on one of its most important and, honestly, least understood parts. It's a calculation that, no joke, quietly prevents fires and keeps our high-tech homes from, well, going up in smoke.
So let me ask you a question. If you had to guess, what do you think is the single hardest working wire in your entire electrical panel? Now, your first thought might be one of the hot wires, right? The ones actually delivering the juice. But the real answer? It's a little more surprising than that. Turns out, the real unsung hero of your whole electrical system is the neutral wire. See, its job isn't to bring the power in, but to carry the leftover power out, completing the circuit. The best way to picture this is to think of your home's electrical system like a giant, non-stop game of tug-of-war.
Okay, so in this game, you've got two hot wires, and each one is a team pulling on the rope. Now, when the loads are balanced, meaning both teams are pulling with the exact same force, that little flag in the middle of the rope barely moves. That's our neutral wire, just chilling, carrying almost no current. But what happens when the load gets unbalanced? Say, one team starts pulling way harder because you just fired up the microwave. Well, now the neutral wire has to carry the difference. It's the ref that has to handle all that extra force to keep the whole game from just falling apart. But this is where that simple tug-of-war analogy points to a very, very real danger. What happens when that game gets seriously lopsided? What happens when we ask that neutral wire to handle way more current than it was ever built for?
Well, the consequences are pretty serious. An undersized or overloaded neutral wire can get hot, really hot. And since these wires are all hidden away inside your walls, that heat can just build up and up, totally undetected. And that becomes a massive fire hazard. Not only that, but it can also cause wild voltage swings that can fry your expensive, sensitive electronics.
To stop this from ever happening, electricians and engineers have to calculate what the National Electrical Code officially calls the maximum unbalanced load. You can just think of this as the absolute worst-case scenario. It's the biggest, ugliest, most lopsided tug-of-war that wire will ever have to deal with.
So how do they figure that out? Well, they don't guess. They follow the super strict guidelines laid out in the NEC. This code is the official rulebook. It's been refined for decades, all to make sure that the neutral wire is always the right size for the job it has to do. And this right here, this is the foundation of it all, straight from section 220.61a. It sounds a little dense, but it's actually pretty direct. It just says you must figure out that maximum unbalanced load. You have to find that worst-case scenario for our tug-of-war and make damn sure your neutral wire is tough enough to handle it. No exceptions. Well, almost no exceptions. You see, the code isn't just about being rigid. It's also incredibly smart. It gets that the worst-case scenario isn't happening all the time. So it has these clever provisions built right in to be more efficient, but without ever compromising on safety.
For certain appliances, things with really predictable power usage like these, the NEC knows they aren't running at full blast 24/7. I mean, your electric oven's power use is pretty predictable, right? Because of that, the code actually allows for a safe and calculated reduction in how beefy the neutral wire serving them has to be.
And that's where this number comes in. The code lets you apply what's called a demand factor. For the load that comes from electric ranges and dryers, you're allowed to calculate the neutral load at just 70% of what's on the label. It's a kind of engineered efficiency that saves money and materials, all because tons of real-world data proves it's totally safe to do. But, and this is the huge but, this is where our modern world throws a giant wrench in the gears. See those smart, predictable rules that worked perfectly for an old electric stove? They don't always apply to the tech that's flooding our homes today. In fact, there are situations where you are absolutely forbidden from making any reductions at all. The reason for this comes down to a concept called nonlinear loads. Think about it this way. An old-school incandescent light bulb draws power in this nice, smooth, continuous wave. But modern electronics? They're different. They sip or gulp power in these short, abrupt pulses instead.
And what kind of stuff are we talking about? We're talking about the very things that power our modern lives. The power supplies in our computers, all that new LED lighting, the fancy variable speed motors in our air conditioners, and of course, the big one, the powerful chargers for our electric vehicles. So here's the absolute crucial point. The NEC flat out prohibits any reduction for these nonlinear loads. The reason?
a risk of something called harmonics. You can think of it as a kind of electrical noise or junk current created by all those power pulses. And here's the scary part. Unlike our simple tug-of-war where the forces cancel out, these harmonic currents from all your different gadgets can actually add together on the neutral wire. This creates a massive hidden danger, and it can overload a wire that by all accounts should be carrying hardly any current at all.
So why does any of this matter? Why have we spent all this time geeking out on one super specific rule in a giant electrical codebook? Why is calculating the neutral load so important?
Because this one single rule gives us a perfect snapshot of the invisible engineering that keeps us safe every single day. It proves that the code is a living, breathing document. It isn't some dusty book stuck in the past. It has to constantly adapt to keep up with our technology, from the simple, predictable electric oven to the complex, choppy power draw of an EV charger.
And that really leaves us with a fascinating question to chew on. As our homes get even smarter, packed with more chargers, more gadgets, more complex electronics, this essential safety rulebook is going to have to keep evolving right along with them. So the real question is, how will it change next to protect us?